I want to make a table of the different classes of molecules that you will have to identify based on their Lewis structures. And then we'll draw some pictures of what the molecule looks like, and I'll point out some things that you'll need to know from those pictures, like what is the bond angle between the atoms and things like that. So let's go ahead and make a chart. So here we go. So what we're going to do is on the left side of the chart, I'm going to write number. Let me see if I can get a better pen here. Number of electron groups of central atom. And then the next row down will be something I call a code. And the next row down, I will write Lewis structure. So we're going to leave some space for that here. And so the next row down, I'm going to have picture. We're going to leave a lot of space for that. And then what we're going to have is LP for lone pairs that are found in the central atom. And then bonding groups for the central atom. And then again, electron groups, which is this first row. I'm just going to repeat that for the central atom. And then finally, the two, maybe the most important rows are something called electron geometry for the central atom. And then what we're going to have is molecular geometry of the whole molecule. Okay, so what we're going to do is we're going to start out by looking at some of the simplest molecules out there in terms of shape. So let's see, here we go. So I'm going to draw a first row here to describe that. So what I'm going to do is describe a class of molecules called AB2 molecules. So I'm going to write AB2 here. And so as you're going to see in a minute, AB2 molecules, A is the central atom, B are the peripheral or side atoms. And what you'll see is that A has a total of 2 electron groups. And so we're going to look here at AB2, and they have a total of 2 electron groups. So to help understand this, let's draw some examples of molecules that are AB2, and you can clearly see the central atom has 2 electron groups. So some examples here would be, for example, beryllium dichloride and carbon dioxide. So let's draw these Lewis structures and see what they look like. So we have beryllium here, and we have chlorines on either side of it, and these chlorines have octets like this. So let's talk about what this molecule is in terms of a Lewis structure. Is it, for example, a correct Lewis structure? And the answer is yes, is because you know that beryllium can have less than the octet. It only needs 4 electrons to be stable. So this is a perfectly fine Lewis structure. Now I want you to notice about the central atom beryllium that it only has 2 electron groups. And the reason why it does is because there are no lone pairs here, but there are 2 single bonds, each which counts as an electron group. So there are 2 electron groups in this molecule. Now, how about carbon dioxide? My hope is by now you can draw a nice Lewis structure for carbon dioxide. It looks like this. And so why is this an AB2 molecule? Well, the central atom is A and the 2 side atoms are B, so it fits in that regard. Now, let's confirm that the central atom carbon has 2 electron groups. And so what you can sort of see is carbon, first off, it has no lone pairs, right? Now, do you remember if you have a double bond, that only counts as a single bonding group. This other double bond also counts as a single bonding group. So we have 2 bonding groups, no lone pairs, so we have a total of 2 electron groups around the carbon atom. So that is fine. Now, what I want to do is sort of draw a picture of what we expect that this molecule would look like. So what is going to happen is, according to VSEPR theory, this is a molecule with 2 electron groups from the central atom. And these 2 electron groups from the central atom are going to get around the central atom to get away from each other as far as possible. So what will happen is, for example, with the beryllium dichloride structure, I'm just going to leave out the lone pairs from the chlorine. These shared pairs from the beryllium and the chlorine here will get as far away as they can from the other shared pairs from the beryllium and the chlorine. And so when they do so, when they get as far away as they can, this angle between the bonds between the beryllium and the chlorines is 180 degrees. The same thing will happen to carbon, double bond to oxygen. So I'm going to leave out lone pairs here just to make my life easier. And so here, again, we don't have 4 bonding groups here. We have 2 bonding groups. One bonding group is a double bond, so we have 2 bonding groups. So we have 2 electron groups as well, because there's no lone pairs. We have 2 electron groups. They will get as far away from each other from the carbon as possible. So the angle they will achieve between the bonds will be 180 degrees. And so we can sort of generalize that by putting an A in the middle here, B on one end, B on the opposite end. So this is the general structure for an AB2 molecule. And so I have a picture of it here, so let's see if I can hold it in such a way so that you can see. And so again, this is a pretty simple idea where the central atom, the yellow atom in the middle, only has 2 electron groups, and they get as far away as they can from each other. And so one goes on the opposite side of the atom, the other goes on the opposite side of the atom. And so the angle between these bonds should be 180 degrees. Okay, so let's finish off this chart. So let's look at the central atoms in these examples. How many lone pairs did the central atom have? We had 0 here. How many bonding groups did the central atom have? Again, bonding groups are single bonds or multiple bonds. And in each case, you had 2 bonding groups. So how many total electron groups are in this molecule? So you add lone pairs plus bonding groups. That should be a total of 2 electron groups. Now, one of the things you're going to have to do is figure out something called the electron geometry and the molecular geometry. And so what the electron geometry is of the molecule is just seeing how any bonds and lone pairs orient in 3-dimensional space. And what you can see is that this molecule here with its central atom has no lone pairs. It does have 2 bonds, and they get as far away in space from each other as they possibly can. When they do, they sort of appear in a line. So the electron geometry is going to be linear for the bonds here. So it's linear for the bonds because those 2 bonds are on opposite sides of the central atom, so they appear in a line. Now, how about the molecular geometry? The molecular geometry is you just look at how the atoms arrange themselves in space. And so what you can see is all 3 atoms are in a line. And so this is a linear, keep grabbing the wrong pen, linear molecular geometry. Okay. So far so good. So now we're going to increase the complexity of the situation. So now what we're going to do is we're going to talk about a class of molecules which are called AB3. And so what you might expect here is at the least you have 3 atoms binding to a central atom. And so if you have that, there will be 3 electron groups. So let me give you an example of such a molecule. So the classic example of this molecule, I'll write example here, is boron trichloride, so BCl3. So let me go ahead and write a Lewis structure for that. So we have boron, and then we have 3 chlorines here. And so I'm going to put in the lone pairs. Okay. And so this is a good Lewis structure because, as you remember, boron being in group 3 does not need to have an octet. It'll be fine with 6 electrons. And so this is a perfectly good structure. Okay, so now what does VSEPR say the molecule is going to look like? In other words, how will these atoms arrange themselves in space? Well, we look at the central atom. We see boron has no lone pairs, but we can see that there are 3 bonding groups, or shared pairs if you want to call it, 3 bonding groups around the boron, but no lone pairs. So you have a total of 3 electron groups. And so if you have 3 electron groups, in this case it's these 3 bonds, these 3 bonding groups, they will, because they're made of electrons, they're all negative charged, they will arrange themselves in space to get as far away as they possibly can from one another. So what they're going to look like is this. You're going to have boron, and then you're going to have chlorine going off in one direction, chlorine going off in another direction like that, chlorine off in another direction. And for them to get as far away, the bonds to get as far away as they can from in space, because they're made of electrons, these angles, to get maximum distance between these shared pair of electrons, you need to have 120 degrees between the angles between the bonds. So let me show you what that looks like. It looks like this. So this is a picture or a model of what boron trichloride looks like. And what you can see is we have a central atom here with 3 chlorine atoms attached. And what has happened is because each of these bonding groups has a pair of electrons, they have gotten as far away as they can from each other in space, and they've achieved 120-degree bond angles between the peripheral atoms. Now, another thing I want you to notice is we flip this on the side, and one thing that you can sort of see is that these 4 atoms in the BH3 molecule are also all in the same plane. So one thing I want you to kind of get used to is how do you represent that these 4 atoms are in the same plane? So your goal is to draw a 3-dimensional structure in 2 dimensions, and so I'm going to show you how to do that right now. And so this is what you might do. So what we have is boron in the center, and we have a chlorine atom here in the plane of the board, and then I want to show a chlorine atom heading out toward me. So what I do is I have a darkened wedge, which indicates that the chlorine is heading out toward me, and then what I have is going into the glass board is I have a light wedge. And so the light wedge I've drawn with dashed lines and I haven't filled in. That indicates that you have a chlorine going into the glass board. So it's as if you're looking at the molecule like this. There we go. Jeez. Okay. So there we, okay, you can fast forward through all this stuff, I'm sure. So we have a chlorine on the right, and then we have a chlorine sticking out toward me, and we have a chlorine sticking out to the board. And so that's how I drew it. So one thing to remind yourself is that all these atoms here are in the same plane. Okay, so now let's figure out the lone pairs on the central atom. You should see that there are 0. How many bonding groups the central atom has? There are 3 single bonds, so it's 3 bonding groups. How many electron groups total? That's lone pairs plus bonding groups. There should be 3. Electron geometry. Again, electron geometry, you're looking at the arrangement of electron groups around the central atom, or just the arrangement of the bonds, whether it be lone pairs or single or multiple bonds around the central atom. And so what you can sort of see is, just ignoring the atoms for a second, just looking at the electron groups, you can sort of see that the electron groups are single bonds, and there are 3 of them, and they are kind of going out in a triangle. But another thing to note is that, again, all the atoms are in the same plane, and so to indicate this geometry of the electron groups, we call this trigonal planar. Now, to get the molecular geometry, we just pay attention only to the atoms and the places they are in space. And what you can sort of see is similar, that you have a triangle of atoms all in the same plane. So this is also called trigonal planar. Okay, we're going to do one more family of molecules and then we'll take a brief break. Okay, so now what we're going to do is we're going to look at another class of molecules. They have a different code. They are A, B, 2, E molecules. And so what is that? That is where you have a central atom, which is A. You have two peripheral atoms, which are B, but then sticking out from the central atom, you also have a lone pair. Okay, as you're going to see in a minute, if you have molecules that can be classified with this code, they have also 3 electron groups. So let me give you an example of one of these kinds of molecules. The example is the nitrite anion. So it's NO2 minus. And so let me draw a Lewis structure for nitrite. So it looks like this. So there's double bond to oxygen, which has 2 lone pairs, single bond to oxygen, which has 3 lone pairs, and then there is a lone pair around the nitrogen. And so, as you might remember, this is just one of 2 correct Lewis structures that you can write, but this is perfectly fine for what I'm talking about now. So, we have this molecule, but can you see why it's called AB2E? A is the central atom, which is nitrogen. B are these 2 oxygen atoms, and then E is the lone pair that the central atom has. So this is an AB2E molecule. Now, what we're going to do is try to understand how do these atoms arrange in space? And it may be not something you might expect. So to figure out how the atoms arrange in space, what you sort of have to do is figure out how many total electron groups there are around the central atom and how do you expect them to arrange themselves in space. So be careful here. We're looking at the electron groups of nitrogen, which is going to be equal to the lone pairs of nitrogen plus the bonding groups of nitrogen. So you can see that nitrogen has 1 lone pair, and I'm hoping you can see that there are 2 bonding groups that are leaving nitrogen going to the oxygens. One of the bonding groups is a single bond. The other bonding group is a double bond. So we have 2 bonding groups and a lone pair, and therefore we have 3 electron groups that are going to arrange themselves to be as far away as they can from each other around the nitrogen atom. So we have a nitrogen here. What is this going to look like? We have a nitrogen here, and so I'm not going to draw double and single bonds. I'm just going to draw a line connecting oxygen atoms. So we have an oxygen atom that is going off in this direction, an oxygen atom that's going off in this direction, and then we have a lone pair. So the way I'm going to draw the lone pair is I'm going to draw it as what it might look like as an orbital. And so I'm just going to draw half a p orbital like this. So it's sort of a propeller-shaped orbital. And then I'm going to draw the lone pair like that into the half p orbital. This is typically the representation of the lone pair. And what I'm kind of hoping is that you can see the lone pair has basically repelled these shared pairs as much as the shared pairs have repelled each other. So the angles here are 120 degrees, about. And they're not exactly that. There's another reason why they're not exactly that, for a reason we'll talk about later. But these angles are about 120 degrees. Now, what does this molecule look like? Here it is. And so what we have here, there we go. I think I got it now. So what we have here is we have a central nitrogen atom in black. And then what we have are these 2 oxygen atoms that are bound to it. And then here I have this sort of bond here that goes to nowhere. Think of this as a bond going to a lone pair, if you will. And again, what you can sort of see is that this lone pair has basically as much repulsive power to these shared pairs going to these oxygen atoms as do the shared pairs have between each other. So this lone pair is good about repelling these shared pairs as much as the shared pairs do. And so that's why it has this 120 degree arrangement. So one thing you can sort of see is also is that you can put this all the 3 atoms and this lone pair in the same plane if you want to. So I could draw a picture of that here. I'll try to be really quick about that. So it might look like this. We have nitrogen, and then maybe going off in this direction is an oxygen. Going off toward me is a filled-in wedge, indicating we have an oxygen heading out toward me. And then maybe going into the glass board is we have a lone pair. And so again, to indicate that the lone pair and these two oxygen atoms are in the same plane, I'll draw a triangle here to indicate that hopefully that they're all in the same plane. Okay, finally, let's do a count. So this nitrogen, how many lone pairs does it have? It has one. How many bonding groups does the nitrogen have? You can sort of see that there are two, right? One is a single bond, another is a double bond. And so this is a bonding group and the double bond is a bonding group. There are two bonding groups that the nitrogen has. So there are two here. So how many total electron groups are there? Again, electron groups are the lone pairs plus these bonding groups. And so we have 3 electron groups. Okay, so what is the electron geometry? So with the electron geometry, what you do is you look at the arrangement of the bonds and the lone pairs. In other words, you look at the arrangement of all the electron groups. And so we have a bond here to this oxygen, a bond here to this oxygen, but you have to, in electron geometry, consider the lone pair. And think of that as a bond, if you will, right now. What is the arrangement of the lone pairs with these bonds? And the arrangement is everything is in the same plane, and it's a triangle here, so this is considered to be trigonal planar. Now, the final thing we have to consider is the molecular geometry. And so the molecular geometry, what you do is you just look at the arrangement of atoms in space by ignoring the lone pairs. So let me cover up the lone pairs here, and let's just look at the arrangement of atoms in space. And what you can see, it looks like the atoms in space, they're clearly not in a linear arrangement, right? They're not all in the same line. There's sort of a bent arrangement. So when you have a AB2E molecule, you will have to remember that although its electron geometry is trigonal planar, the molecular geometry, which is just looking at the arrangement of the atoms in space, is just bent. So you write bent here. Okay, next time we will go over families of molecules that have 4 electron groups. And so thank you for listening to that presentation. We will see you next time.